Hi everyone. In this video, I'm going to be talking about some of the ways of making amines. So the first one you'll learn is called reductive amination, where you take an aldehyde or a ketone. In this example, I'm going to be using a ketone, but this is just as valid for an aldehyde. You take a secondary amine, okay, and then you use catalytic amount of acid, very small amount of acid, along with the reducing agent, a mild reducing agent. Most common one you're going to be seeing is sodium cyanoborohydride. Another one you may see in this class is sodium triacetoxyborohydride. Okay, and what this gives you is amine that is appended to the ketone you started with. Okay, so half of this reaction is something that you guys are very familiar with. That is, if you take an aldehyde and ketone and a secondary amine, right? These two right here, right? With the catalytic amount of acid, you already know what happens, right? All you do is replace the C double bond O you have with the C double bond end, okay? So how does that look like? That looks like this, right? Form an iminium. So this iminium, so this is iminium is formed when you have a secondary amine. If you have a primary amine, then you form an imine. Okay, so this is the intermediate in this reaction. So when you form the iminium, after you form the iminium, when it's treated with this reducing agent, sodium cyanoborohydride, the only thing that you should be getting out of it is, you don't care what this is, you don't care what that is, you only care what this is, just a mild source of H minus, okay? And you know that C double bond O, as I've mentioned before, C double bond N is parallel in reactivity to C double bond O, okay? They're very similar in reactivity. It's this carbon right here is the electrophilic spot, and you have anhydride, which is a nucleophilic, and then they go react with each other, and that give you the product. All right, and it's important to learn how what's the mechanism of the formation of iminium. So I'll show you that. Okay, so as you guys notice that you're using a catalytic amount of H plus. The reason for that is, you guys may already know, ketones aren't very reactive, right? Because they're hindered and they're not as reactive as the aldehydes, right? The point of acid is to activate the ketone, make it more electrophilic. So the first step is the carbonyl group will grab the H plus. Okay? After it grabs the H plus, you'll get this species called an oxonium. And when you pronate a carbonyl group, you make this carbon even more electrophilic. The reason for that is, if you draw the resonance structure, right, you will have literally positive charge on that carbon. That's what makes it so electrophilic. All right. So now that you've made it more and more electrophilic, now the nucleophile could come and attack without any ease. Okay. So the nitrogen is a nucleophile, goes and attacks. So that gives rise to this tetrahedral intermediate, which looks like it looks like, right? And as you could see that it's supposed to form an iminium, right? You're completely supposed to replace the C double bond O with C double bond N. That means that your oxygen, this entire oxygen is gone, right? That tells you that, what that tells you, that this shall be your leaving group, okay? But you guys already know that hydroxides are bad leaving group, and you guys know how to make it better, right? How do you make a hydroxide into a better leaving group? You add proton, right? You make it into water to make it into a better leaving group. But before we add proton to the oxygen to make it into water, we have to remove the proton from the nitrogen. And then the first time you use the acid, right here in this step, the conjugate base is just laying around there. So use the conjugate base to deprotonate the proton from nitrogen, okay? And that does two things, right? Now it makes firstly, it makes the proton now available for the oxygen to take. Secondly, it gives nitrogen the lone pair back so it could push out the leaving group. So this step, the oxygen will take the H plus, and you guys already know what that becomes. After the oxygen takes the H plus, it turns into our good old friend water, okay? And you know that you can't just, this mechanism, it doesn't operate in SN1 fashion. So the water can't just pop off and form a carbocation. What really happens is the lone pair of nitrogen go and push out the water. And you guys should practice this mechanism multiple times because you'll be seeing so much of it throughout the quarter, you're gonna get tired of seeing it. Almost all the acyl substitution mechanism works very similar to this route. That's how you make the iminium ion, okay? And after the iminium is here, the sodium cyanoborohydride will reduce it, and you'll get the amine in the product. Now you guys might be asking, why do we use, sodium cyanoborohydride? Why can't we use our good old friend sodium borohydride or our best friend lithium aluminum hydride, right? The problem with that is you guys know that both lithium aluminum hydride and sodium borohydride, they like to reduce aldehydes and ketones, right? So if you were to put either of those in the pot when you're running this reaction, before you even have the ketone and the ketone, aldehyde, and the amine react to form the imine or iminium, it will reduce the ketone or aldehyde, right? Sodium borohydride will go reduce the ketone and aldehyde to make it into alcohol. If you do that, this condensation will never take place to form this thing, and it will never go and make an amine. That's why we need to use a milder reducing agent, okay? And the reason why sodium cyanoborohydride is a milder reagent, think about it. When you learn about sodium borohydride, right, it's Na plus and it's hydride minus, right? Borohydride is the minus charge. So this is a pretty good nucleophile. But what happens when you make sodium cyanoborohydride is you replace one of this hydride with a cyano group, CN. And you guys already know this is an electron withdrawing group, right? So the electron withdrawing group is pulling some of the negative charges away from the hydride, making it a little bit more milder, okay? Another way of making amines, and this is the primary way of making amines, is through cyanides, right? So if you treat cyanide with lithium aluminum hydride, it gives you amine. And at first glance, the product might look a little weird, right? But whenever you have cyanide, don't ever forget that cyanide comes with an extra carbon, okay? So if it helps you, draw out the carbon and count it so you know how many carbon the product should end up with, right? And whenever you see cyanide, you should also think about, right, C-O, carbonyls. I told you guys that carbonyls are very similar in reactivity to imines and iminium, C-N. So cyanides, right, are also close to the C-N, right? Except it has triple bond, it's C-N. Just like you could reduce iminium, C-N with hydrides, you could also reduce C-N with hydrides to give rise to an amine, okay? Another method of making amine is reducing amides, okay? And you also need lithium aluminum hydride for amides. And this might look a little odd to you because the oxygen disappears, right? And before, anytime you have used lithium aluminum hydride with any sort of carbonyl C-double-O, you always reduce the C-double-O to a single bond O. This time you got rid of C-double-O altogether. And the reason why that happens is initially, oops, in the hydride attacks, you form this intermediate, right? With like the lithium plus being the counter ion, okay? And after you're done with the first reduction, right, when you do workup with water, okay, so if you add water, so even if you add water to the solution, it's still basic. And you guys already know that the nitrogen is more or less electronegative than oxygen, right? That means nitrogen does not like keeping its electron as much as oxygen does, right? So that's why this nitrogen will go push out the oxygen, right, to form this iminium, which will then get reduced to the amine. Oh, and I don't think you use water here. My bad. This still needs to be under the. So this oxygen is just complex with the lithium and the other thing, and it just pushes it out. So it also goes through this iminium intermediate to get to the amine. Okay. And on the Google Drive, I have a 26-page summary on everything you can imagine about amines. Okay. So please take a look at it, and we'll be going over more problem from that in my office hours.